My name is Jerry Harp. I'm an astrophysicist here working in Joel Tarter's group on doing SETI observations. And I've also been a member of the team that built the ATA, which is having a lot to do with Jack, because the ATA was in many ways his brainchild. I'm very pleased to introduce Jack today. He has been professor of astronomy and electrical engineering at UC Berkeley for 1 year longer than I've been alive, from 1960 to 2005. And he's now emeritus professor at UC Berkeley in the graduate school. He's a member of the National Academy of Sciences, member of the SETI board, so he helps run this institute, and he has had many awards, most recently the very important 2008 Van der Poel Gold Medal of the International Scientific Radio Union. International. So, and why did he get the gold medal? Here's what the citation reads: pioneer of millimeter wavelength interferometry to investigate astronomical objects ranging from solar system planets to galaxies at the edge of the universe with spectral and angular resolution. So with that, I'd like you all to please welcome Jack Welch.
One of the things we did do at Berkeley was to develop a millimeter array, and that's what the citation was about. We started that work sort of in the late 60s, and we built it up to a fairly big thing. It's now part of the Karma array in the Inyo Mountains. And all of this was now led up to ALMA, the big millimeter array that's going in Chile. So that was kind of a start on that. But now, for this, I've switched over to doing centimeter wave work. And we have built the Allen telescope array and are using it for SETI, mostly now, but also for other science. And so what I'd like to do is tell you a little bit about some upgrades we've done to this, which should make a really big difference in what it can do. And so here we are, the group that's worked on it, myself, Matt Fleming, very good mechanical engineer, Greg Gargiol, Rob Spencer, Dave DeBoer. Sandy Weinrib actually is at Caltech, and he designed the little chip, which is the low noise amplifier in the feed. That's very good. All right, so let's get going. Here's a nice picture by Seth, I think. He's wandering around somewhere. I'm pretty sure it's Seth's picture. They're so great. Well, anyway, this is the ATA. There's 3 of the 42 two antennas that you can see. And so I'm going to say a little bit more about those as we go along. This is a close-up view. There's a photograph and a drawing. Now, the thing on the left is actually a drawing. And let me say just a little bit about the optics for this system, because it's a little unusual. This is an offset Gregorian, and therefore it's a 2-mirror telescope. And the way it works is that the primary, which is on the right, let's see if I can get this to show here. That says you'd notice. Okay, well, then the primary that's on the right and the secondary is on the left. The primary is a piece of a paraboloid. Secondary is an ellipse. And so what you do is to arrange that the focal point for the paraboloid coincides with one of the foci of the ellipse. And then rays that come in from infinity all end up going to the other focus of the ellipse. And that's where we put the receiver. So that's how that works. Now the receiver is down low, down in here. And you might say it doesn't look like it's in the right place to be at the focus. The point is that this thing is offset. Rays actually come in from this direction here. Okay? They completely clear the secondary and the feed. They come in this way, bounce off this, and then go into the feed. The feed is down there kind of down in this little valley. And what that does is to protect it from the ground noise. So in order to do that, what we've done is put this metal shroud all the way around. It's roughly a cylinder, joined between the 2 feet, the 2 mirrors. And this thing is down in there. So the feed, which we want to protect from interfering noise, is very well protected in this arrangement. So there's no orientation of the antenna that you can put it to in which the feed sees the ground, which is a serious source of noise to be avoided. And then the picture on the right has the shroud that's on it. In addition to the shroud, it has the cover. It's Sumbrella, that's what it's called. It's an awning material, and it keeps the snow and the rain and everything out. So this is the basic system that we have. And a few numbers about it. There are 42 antennas. The field of view, which is fixed by the diffraction of the individual antennas, is lambda over 6. So at 20 centimeters, it's 2 degrees. So that's the hydrogen line. The other number is the resolution of the array, which is quite a bit bigger than that because it's a collection of these antennas set out there. And so the resolution of that is lambda in meters over 300. So it's a factor of 50 larger, or smaller rather. So put a couple of numbers, 2 degrees at 21 centimeter line basically. For the field of view, 2.4 minutes of arc for the resolution. The array has, in fact, 250 to 2,500 pixels, independent pixels. When you form a map by doing all these cross correlations between the antennas, and you have to do that with the antennas arranged well enough so that you get a good sampling of separations and orientations in the connections between pairs of antennas. And if you arrange that well, then you get a nice point spread function, sort of Gaussian, and you get 2,500 Gaussian pixels in this 2 degree patch on the sky. So that's the basic operation. Now here's a picture. Let's get onto the feed a little bit. Here's a picture of the feed. Photograph is on the right, and a drawing is on the left. The antenna, this feed, it's a log periodic feed, which is one class of radio antennas. It's a little bit odd, but it has properties of very wide bandwidth if you can make them work. And the way it works is that the signals are received at some point on the feed, depending on their wavelength, and that point moves if you go to a different wavelength. So let me get over here so I can actually point at it. This is the low frequency end of the feed. The tines in the feed are about a half wavelength long. And there are these tines, and they're over this pyramid. That's part of the feed as well. The shorter wavelengths are received down here. Now, the log periodic character means that it's self-similar structure. And the self-similar scaling is 0.96. So if you took this thing and scaled it by 0.96, it goes back into itself. That's the characteristic. Now, it turns out that if it works well within that small log period, meaning giving good patterns, good impedance in one log period, then it'll work for all wavelengths, limited only by how big you make it at this end for the low frequencies and how small you make it at the other end. That's the limitation. So this is a tremendous capability. On the other hand, since it receives different wavelengths at different places, you might wonder how will this connect into the telescope? Does it mean you have to refocus it for every different wavelength? Well, you have to do to a certain extent, but not too much. And I'll say a little bit more about that in a couple of minutes. And this shows the blow up of what's inside. The little low noise amplifier is inside, and its connection to the feed is over here. The input terminals are at the end, which in fact is very awkward because that's the direction from which it receives. So you can't put a big boxy receiver right there. It just gets in the way. So that's an awkward feature. You like the terminals to be at the back end, but they're not. And so signal is received somewhere. It runs along, forms a wave running between the tines and the pyramid, runs to the end, hooks onto the wire, and then comes back into the LNA. And so that's basically how it works. Okay. Now the issue, this will address the issue a little bit about the focusing. How much of a problem is it? Now, these are focus curves for different settings of the focus. If you focus it so it's correct at 12 gigahertz, that means you're down near the tip here. Then how does it work at other wavelengths? Well, the 12 gigahertz is the blue one, and you can see it's pretty good all the way, in fact, all the way down here to 1 gigahertz. It's still only down about a dB, which is not bad. And so you might, probably what you're going to do most of the time is focus it at 10 or 12 and leave it there for a lot of the time, because you have good sensitivity everywhere. If you want to do an H1 line study at 1.5 gigahertz, that's not so good. If you're doing nothing but that, then you'd focus down here, like that 2 gigahertz, and then you'd have, you know, full sensitivity down there. So you can do that. But for the most part, you can work at all sorts of frequencies over the whole range, and it works well without having to shift the focus around. So you can do those things simultaneously. So that's a great help. Now I'm going to say a little bit about noisiness in here, and so I want to describe what it is I'm talking about. We're going to talk about the noise that's there, produced by the amplifiers or whatever, in terms of a noise temperature. And we do that by saying, well, the power of the noise is Boltzmann's constant times that noise temperature, whatever it needs to be, times the bandwidth. And so instead of talking about the power in watts or something else, some other thing, we'll just use temperature and noise temperature. That's a little easier to deal with. So if we think about the low noise amplifier, for example, it has an input and an output. And if you put a signal through, you see it amplified, but it's a little bit of added noise. And we put the noise in as if it's another input to the input of the amplifier. And that describes the basic noisiness of the amplifier and what the add-on is. Now here's another set of relations which tell a little bit about what we can do to improve the noise situation. Basically, the reason that we want to make an upgrade here and have done so is that the amplifier and antenna is a little noisier than we'd really like. So what can we do about that? Well, it turns out the noisiness comes about because of the fact that the metal of the feed is a room temperature. And so associated with the resistance, surface resistance, you get a little extra noise from that. And here's the way it goes. The added noise, temperature, depends on the physical temperature. That's just the black body function of the metal, times the resistive loss. So what's that? Well, if you have a wire, say the center conductor of a piece of coax, because of the finite conductivity of the metal, you have the current flows along on the wire. And so there's a sort of surface resistance to that. The fact that that's finite means that, and if it's at a real temperature, you get noise. And so that's this times this. The resistive loss goes as the square root of the resistivity. And we use copper now for the new one. Copper, if you cool copper from 300 down to 70 Kelvin, the resistivity falls by an order of magnitude. It's a huge effect. That's one of the reasons we use copper. So we're going to get a factor of 10 here. It's a square root in this effect, so the square root of that's about 3. But we're going to lower the physical temperature from 300 down by a factor of 4. So altogether we get about a factor of 12 reduction in the noise if we could just cool it down. Just cool it down. So that's what we did. And how could we do that? Well, put it in a bottle and evacuate it, cool it down. You can get it down to 70 Kelvin if you do this. And then all the good stuff that I just talked about takes place. Noise goes down. It's just what you want. And so we did that. Actually, there are some more details about how to do that I'll come back to. But then we made some measurements. Now this is a very, very busy slide, but let me explain it. The way we do a measurement on our system is we want to find out what the noisiness of it that's inherent. We hook it up to an ambient load, 300 Kelvin load, and make a spectrum. And then we hook it up to a 70-degree load, liquid nitrogen, make another spectrum, take the ratio of them, which is the difference on the log plot, and that's called the Y factor. And you can dial out what the temperature is from that. So for example, if you measure a Y factor of 4.5 in that pair, it means that the noise that's being added to the system is 40K. Or if it's 4, it's 64K and so on. If it's really good, you know, if it's way up here, it's quite small. So this is a perfectly good way to look at what you've got. And what we have on here is two things. One is the feed as it is now, this guy down here. So what can you say about that? Well, it really doesn't work very well once you go beyond about 8 gigahertz. And that's because the tip is too large. And so we're getting numbers in kind of in here, 64 Kelvin for this. But then the total system temperature takes into account the background from the sky, mostly. So that's another 10 Kelvin, roughly, more or less independent of frequency. And so I've added that number over here. And so if you want to know what the system temperature is, like that, for this along this line, it's about 74 Kelvin. Okay? So this is the old feed. Its bandwidth is narrow, and it's kind of noisy. This is the new feed. Now, it's a little busy here. These are all different bias settings for the LNA. You have to set 3 voltages to get the thing to operate properly. And it turns out that how you do that makes a big difference on the result. So all these different curves are for the different bias settings. So you just find the best one, which is the red and the blue, and that's the one we use. And so how did it work? Let me point to this line right here. That's a calculation I made before we did the experiment, just taking the simple idea of cooling down the metal. And I calculated what we should get if that's most of it. And it's pretty much the story. So this is really good. So how are we doing compared to anybody else? Well, the most recently upgraded centimeter wave system is the VLA, now called the Jansky VLA. And they work very hard. They have very good receivers. It's a terrific instrument. They say that their best result is at X-band, which is 8 to 12 gigahertz right here. And we're doing actually a little better than they are. So the system now is absolutely top of the line. That's really great. And you can see that, for example, up in this range here, we're talking about, 10 Kelvin or something for the receiver. And for the total, something like 20. Now, we don't measure the lowest frequency ones because of the way we do it, and I'll explain that a little later. But nevertheless, this is almost perfect. And it's hugely better than this. So it's dynamite. So we'd like people to buy us a whole lot more of these things so we can put them on. Well, actually, it's not quite as easy as I described. Just stick it in the bottle and pump it down. So I'll tell you a little bit more about what we had to do to get to that. So here we have the, it's really a nice drawing of the whole system showing the feed in here and the refrigerator here. There'll be a vacuum pump in here in the glass bottle. And then here's a couple more photographs. This just shows the refrigerator in the back. But notice there's a funny dunce cap on there now. And that's because the glass is not completely transparent to the radio waves. So we have to do something about that. So this is a little anti-reflection coating, a little dunce cap. And so it took a while to figure that out. And these curves show what the glass does. The glass bottle is about 1 millimeter thick down. It's a 6-inch diameter sphere. It's about 1 millimeter thick. That's only 40 thousandths. And we said, well, if you go down to the drugstore, you can buy a small light bulb, and it's half that. do you want to go down there? And they said, no, we don't think we can do that. And so this is where it is. And so we have to deal with this match problem. If you have the glass only, what this curve shows is the transmission through the glass dome. If we have nothing but just the glass there, it's this curve here. So up to, and these are pretty good transmissions, 98%, 96. It's not too bad here. But if you follow down to 15 gigahertz, which is down here somewhere, it's like 70%. That's really not very good. So then we played around what to do about it. And we had this idea of standing off this layer of plastic. And so we just tried all sorts of thicknesses and separations until we got one that we liked. And this just shows two of them. This is with a 4 millimeter gap. And this is 1 millimeter thick, and this is 1.2. It's a polyethylene layer. So this is actually pretty good, you see, because instead of being really lousy down here, now it really works all the way down to 15 up here.
Why does putting the layer, why does that increase the transmission?
Well, it's an interference effect.
Oh.
Really, it's just, the wave goes through and it bounces off the first one, but then the second one, it comes back with a little bit of phase difference, and the interference effect makes it work. So it's a slightly different anti-reflection coating result, but it works just like a champ. Anyway, so this is really good. The worst place along in here is right in the mid band, but even that's still 96%, so that's not too bad. So that's pretty good. Now, here's a test to see that it works. These are pattern measurements on the feed. We went into an anechoic chamber with a horn at one end sending a signal down, and then we rotated our feed around, measured the patterns. So what can you see? Well, the part of the spectrum that we expect to be worse is in the mid-range. So we plotted those patterns for 5, 6, and 7 gigahertz. These are 3 colors, and with and without the glass. NB means no bottle. And this part right here corresponds to the mirror that this thing has to feed. And we also did a calculation, 7 gigahertz. You can see they all agree almost perfectly well. So this works fine. This anti-reflection coating thing works just fine. So that's fine. It took a while to figure this out, but these things all do. So let's go back and look at what the feed has become now and the new version. Well, for one thing, we don't have this little dewar down inside. The whole thing's around the whole thing. So it's a whole lot easier. So the mounting is a little different. Here's the mounting of the chip, and we send coaxial cables down to the end to hook onto the antenna, and that's how the rest of that goes. We can use small coax here. It's 30 mils coax with 2 mil center conductor. So it's 95 ohms. About human hair size. We can do this because it's cold. It's at 70 Kelvin. And so its losses are negligible. That works just fine. And then the other thing we have to do is to look at how we connect at the tip end. So we come out at the tip end with our 4 pieces of coax, and then a lead comes out to this arb, one here, one there, and one there. The trouble with this, just having the lead there, is that that's a lot of inductance at high frequencies. It would just kill it. So we did a little thing which turned out to work well. See these blue blocks? Those are capacitors. So we split the line in 2 and put a blue block in of the right size. It's 0.05 picofarads. And not only is it 0.05 picofarads, but it's got a little bit of self-resonant inductance in it. So it turns out that's just exactly the right amount so that you get a low-pass Chebyshev filter, 15 gigahertz, with these parts in there. So that just completely takes all this away. That took a little thinking, too, to figure out how to do that. But anyway, that works. And I think the next slide shows. What's this? Ah, good. The scale, this is about 200 thousandths across here. It's very small. It's much smaller than on the original feed, actually, because we really wanted to go to shorter wavelengths. So our mechanical engineer can do anything, even this. And it's quite amazing. But it's very small. So this is a plot showing the echo that we get off that ending there. And if you remember back a little earlier, I showed the noisiness of the low noise amplifier. It had a little bit of a wiggle in it. So that's for a 10 dB echo. So that says you want to have this echo 10 dB, minus 10 dB or better. And so here's minus 10. And a couple little points stick up, but not much. Basically, it's all the way up to 15 gigahertz is a good match. So yeah, right. Hooray! So we went on and had a beer on that one too. So that looks very good. In fact, this includes the balun that we had to use in the experiment. It's a balanced system. Our network analyzer is unbalanced, so we made our own fancy balun. So any of the balanced stuff is in there too. So that's really great. That's really good. So that worked. And here's a picture that shows a little bit about the testing that we do. We actually put some of that umbrella around the glass dome because it's very big, and you're standing right there next to it, and it's only a millimeter thick. So in fact, we did some experiments with seeing how easy it would be to have an explosion or an implosion. And we didn't do it with this thing. We got some carboys, put the umbrella around it, hit it with a wrench hard to see what happened. And this caught all the bits, almost all of them. So it's really good stuff. I really recommend it. It's great for awnings on your back porch. Anyway, so it's great. So that's the way we do that. And after a while, and after several months, and it hasn't exploded, we feel pretty comfortable walking around that thing. And we haven't blown up one apart. But anyway, what's shown in here is how we do the noise measurement. This is we point the thing down into this box with absorber around it. So this is the match load. And then we have another box that we bring over, which has foam around it, but it's got liquid nitrogen around it inside of a metal bucket. And we can only do the tip, but that's most of it. So we don't do down below about 1 or 2 gigahertz, but we know from experience if it works well at the high frequencies, it's no problem at the low frequencies. So we in fact, the way we do this is that we take this out and bring this out. We don't move anything because we found if you wiggle cables or anything, it causes trouble. So we bring the loads in like this. It's also done in the screen room. This is done out at Antioch. And I mean, the television is overwhelming out there. So we have to do everything in the screen room to get around that. This works just fine. Anyway, so that's a noise test chamber. So that's all great. So that all worked. And here we are back to this thing again. And so let me just say a few more things about this. I may have said many of them already, but the fact of the matter is, I guess the one thing I wanted to say here, maybe I'll say it again, these results are as good as any centimeter wave antenna system anywhere. Okay. And maybe I should say at this point, what were the motivations for doing this? Well, of course, we'd like to fix up the ATA, and we're doing that essentially by this work. But in fact, a lot of this was funded for the square kilometer array, which is a huge array that's planned for the future, probably to be constructed beginning in 2020, something like that. This square kilometer array means that the collecting area will be a square kilometer, big number. And it'll be a big array of modest antennas, and this is going to be the feed, I predict. I mean, we were funded to do this, and of all the things that are tried, this is the one that's worked out the best. So this will probably be the feed for that. But in the meantime, we also hope to do some more with the ATA, with the C. Okay, so let's think a little bit about what we can do. Well, SETI observing is very important here. It's important in any case. What does this give us now? Because you see we have this coverage from 1 gigahertz to 15 gigahertz now. It was before 1 to 8. 1 to 15, very low noise temperature. So if we put those edges there, you can see that the terrestrial microwave window is nicely covered by this feed. Okay? So what is it? This is the galactic synchrotron radiation over here. And this is the atmosphere. Water vapor here, oxygen, more water vapor. And from the point of view of thinking of SETI observing, this is probably a good thing to look at, because if there are stars out there with other people on them, they're in the same galaxy we're in, so they're going to have this part of the problem. And if they're like us, that drink water and breathe air, their atmosphere is going to look like this too. So this is the right part of the spectrum for doing SETI. And so that's what we'll be doing. Okay, now let's think a little bit about the SETI that can be done nowadays. We have the Kepler stars and several hundred others that had been found, sorry, planets I should, but several hundred others that were found by the reaction on the velocity, radial velocities of stars. But the Kepler batch is really tremendous. And so here's the field of view. I think there are 92 separate CCDs in here. Each one of them has 1 million pixels in it. Incredible. And what's shown in this picture is the different releases, the June 2000 up to the February 2012, which is of course very recent. That's what the coloration is in here. Now, what kind of stars are there in this? This shows you which are the ones that are most interesting. They're altogether about 2,400 of good planets around stars. The ones that are less than 1 1/4 Earth radii, the really interesting ones, number about 10% of that group. So these are the first ones you want to look at. And the range of frequencies, well, anywhere from 1 to 15 gigahertz. So these are the good ones. This particular thing doesn't show you in the color which ones they are, but anyway, they're reasonably well distributed among them. So for the ATA, we can observe these things in 2 different ways. The one that we've been using mostly now is to form beams with the Allen telescope array. And what that means is that we just add up all the signals from each antenna and put in the right delays so it corresponds to a beam in some direction. So that'll be a beam on one of these stars. We at the moment are using 3 beams. We think we'll be up to 6 before too long. And so we'll be able to look at the separate SETI stars, or the separate Kepler stars, in each one of these pointings. Now this is the angle that corresponds to the resolution of the individual antennas. So that's the field of view. And 40 pointings at 3.5 gigahertz, because that defines the size of that, covers the whole lot. So that's the job. And of course, there's a lot of frequencies to cover. But basically, this is the program that's going on now to do these things. Now, there's another interesting thing we can do. We've only just, Jerry and I were talking about this the other day, that another thing which we hadn't been doing, but looks like it might be a good bet. See, the traditional SETI observing adds all these signals up, so you get a signal of up to 50 megahertz, and you can analyze it any way you want. So we have this equipment that analyzes it all the way down to 1 hertz elements. So that seems like a good thing to do. But on the other hand, our communication friends, experts, are telling us that RFI is ever worse here. And so the way communication is being done on the Earth is by spread spectrum. So you actually take whatever your bandwidth is and you spread it out in some way and code it so that you can make something that gets through. And so they're saying anybody out there who's been around as long as we have, probably longer, are having more and more trouble than we are. So they're going to be using spread spectrum. So it's an interesting idea. Well, that means you can look for really wider signals than just 1 hertz. And now it begins to be something that our correlator can do comfortably. So the correlator can look for wide signals. There's another thing here, which is very important, and that is polarization. Man-made signals that go into antenna are going to produce a polarized signal. Now, any antenna has two pairs of terminals on them. It could be for this polarization and this polarization, or it could be right circular, left circular, right elliptical, anything like you can have different combinations, but you get two polarizations. If you put one powerful transmitter on here, you only get one polarization out, no matter how you hook it up. So my bet is that the SETI signals could be very strongly polarized. And polarization is something that the correlator will see. It normally just sees the total power in the different spectral elements, but it can detect polarization very well. So we're now looking at another nice thing to do is to look with a wideband correlator in every one of these pixels with about the right bandwidth and see if we can find polarization. So that's another kind of exciting thing we're looking for. So, all right, what else can we do with this thing? Well, what other radio astronomy can be done with it? So let me tell you about a couple of things. I'll talk about something rather close to home and something rather farther away. One of the things I've been interested in for a really long time, and I have to say it's a really long time because I'm that old, I guess. Anyway, one of the things we did at Berkeley in 1968 was to find that there's water vapor and ammonia in the atmosphere, in the galaxy, not in our atmosphere. You know it's in the atmosphere. We found those things in the galaxy. It was a really exciting discovery. And what happened was a huge follow-up in which many organic molecules are found. I mean, there's 100 or 200 of them are known. They're out there. One of the side effects was that we found out where stars formed. So what do I mean by that? Well, before we made this discovery, you could look at young-style stars, T Tauri so-called, and they didn't line up with H1 clouds in radial velocity. So that's not where they were formed. Where were they formed? Who knew? But when we found the ammonia, we had to know that there was molecular hydrogen there to fire up the ammonia by collision. It had to be there. You can't see it, but it had to be there. So we found molecular clouds as a little side thing. And then shortly after that, one of our colleagues said, well, let's compare some radial velocities of young stars with the molecular clouds. Found things added up perfectly. So at that moment, we found out where the stars formed. So there's been a huge progression over the years of interesting things to do. And for example, this is a region in which low-mass stars are forming. They're all over the place. It's a huge region. This is the beam size of the ATA in this big region. Great place to study. And so now what we're interested in knowing is how does Mother Nature decide how many of different kind of stars are formed? We don't really understand how that works. And so this is something we're headed towards. And so here's a place where we could use the ATA very nicely. It has a huge field of view. So here's our goal, find the pre-protostellar cores that have not yet formed stars. There's a lot of action with things like the millimeter systems of like ALMA, looking at these things after they're forming, and there are disks and so on, and you know, what are the last parts of it? But the earlier stages are still not understood very well, so that's what we're going here. So find the pre-protostellar cores, and there's the field of view. So that means when you point the ATA at it with its small 6-meter dishes, the field of view is still only a small piece of this. So it's you know, with things like the EVLA, you know, the fields are tiny. So this is very well placed. So we hope to model core density and velocity and see if we can understand how the collapse process works on the larger scale. Right, so there's a summary. What processes determine the final mass of the star that is forming? So we don't know that, so this is one thing we're headed for. And here's one tool that we could use. This is a long-chain molecule, HC3N. And the 1 to 0 transitions is about 9 gigahertz. There are 3 hyperfine lines there, so you can look at the relative strengths of them, figure out densities and temperatures. So this will be a good thing to to be making maps of. How well could we do? Well, if we had the new feeds on, you'd get This is rude. Oh, finally went away. Signal noise would be 20 to 1 in a 1 hour integration on this stuff. That may seem slow, but that's not bad at all, actually. That's a pretty good signal to noise. So this means that the ATA, with these feeds, could really wail on this stuff. And so it's something we're looking for. Here's a related thing. Here's another long chain molecule, HC5N. And there are quite a few lines in the band that can be done by the ATA. The frequencies are listed on the right, and the transitions on the left. And with 4 correlators for which we have the capacity, you could do all the first 4 lines all at the same time, looking at the same cloud. And so what can you learn from that? Well, here's an example. It turns out that if you take the ratio of the 4 to 1 line, or 4 to 3 line, to the 1 to 0 line, if you just take the measured ratio of that, you get a quantity which is almost independent of temperature. You need to know what the temperatures are, but typically they'll be in the range, 10 to 30. In that range, you can take that ratio and find out what the density is without having to know exactly what the temperature is. So this is just one of the many kinds of games you can play with the observations, the sort of thing we do. So that is, we'll be making these 4 maps, and then from them we work out these ratios, and then now we know what the run of density is. That's the kind of thing we need to know. We get the temperatures from the excitation of the lines, but we get the run of densities in this case. So this project would be very nicely done with the ATA. The next thing I want to talk just for a few minutes about is looking at really large distances at high redshift. Now, there's a lot of interest in trying to understand how the universe began and what its structure is and how it's going to evolve. And we know that there's dark energy and dark matter out there and all these things. We don't know too much about them. But anyway, we can learn a lot by looking back in time, which is the same as looking at great distance, and measuring what's going on there. And so, for example, the Sloan survey has found a lot of high redshift items in their photographic results. And so you can take one of these directions, and then knowing the redshift there, you would know what the shift of say, a carbon monoxide transition would be related to that. And so some of that work has been done. And in particular, one of the highest redshifts found is about 6.4. And so those redshifts are pretty well determined optically. So you can take them and you take 1 plus z and divide it into your CO frequency, and that tells you what you'll get. So you take 1 plus z, if z is 6.4 for this thing, you find that the 3 to 2 transition of CO shifts down from 350 gigahertz down to about 46 by just making this little calculation. So people have done that at the NRO and then gone out and focused the array on this direction and set up the correlator so that it was going to look for a 46.8 gigahertz signal. And by golly, there it was after quite a bit of integration. There it was, bang. And so it's clear what it is because the numerology is very particular. So what they found is carbon monoxide, not the high frequency stuff or the low frequency hydrogen, but rather the carbon monoxide in a galaxy. And in fact, you can calculate from what their beam width is, how big is the patch on the sky back there. And it turned out to be about 350 megaparsecs. Everyone knows what a megaparsec is, right? It's a big distance. But anyway, it's a reasonable size. It's about the size of the local group of galaxies that we're in. Ourselves and the Andromeda Nebula and the other guys. It's about that size. So what it tells you is that they made a map of something about that size out there. And somewhere in there was this really bright hydrogen line. And so they even had a little bit of a map in there. Anyway, so this was really quite a nice discovery. So then I figured, well, what could we do, like that as well? We can't go to 46 gigahertz. It would be 15.5 for the CO1 to 0 line. We could do that one. Okay. And so based on their observations and knowing what the signal strength was, I figured we could just barely detect it in about 20 hours. So it would be fun to do. So what would we learn about with our system? Well, our field of view is, the 6-meter antennas on this 15 gigahertz line, and not 25-meter antennas on a 46 gigahertz line. So our field of view is huge compared to what they had. In fact, it's about 4.5. Do I have the number correct? 4.5 megaparsecs. This brings me to my next picture. Well, there's the picture. It's about 4.5 megaparsecs is the size of it. So what could that be, And here's a picture of the Coma Cluster. It's a giant cluster that's kind of in the foreground. It's one of the biggest things you can see out there. It may be hard to see what it is exactly, but there are, I think, 10,000 or more galaxies in this cluster. And so what it says is that if they had bumped into something like the Coma Cluster, and they only saw a little piece over in the corner, like this, we would see the whole thing with the ATA. And it's a pretty good bet there are probably some other really bright molecular line emissions too. So we could begin to work on such things as this kind of a development, basically. So, let's see what else. Yeah, well, that's one last thing. One thing I have to fess up to is that we got the money to work on this feed from the NSF in support of this square kilometer array project. And actually the money came through Cornell, and they passed it on to us. And we worked on this feed. Several other things have been done. For example, Matt Fleming is working on the antenna for the square kilometer array. It's got a really nice design going, and it's going to get built. But in any case, this picture shows, this is a picture of Matt's antenna in large number as it might look as part of the square kilometer array. These are 15-meter dishes. It's kind of a funny looking thing. But this is the, it's an offset Gregorian, just like the one we've been doing with here. And here is the Gregorian here. And here is some stuff which turn out to provide the shroud, actually, so that the antenna doesn't look at the ground in any direction. But that's all underway. And so this is something we may see. I don't know if I'll be around to see it. But anyway, this thing, construction of this thing is probably going to start somewhere around 2020 for the square kilometer array. This is probably going to be the antenna. And this is probably the feed that they're going to use. And I think that's my, yes, last story. Oh.
Thank you, Jack.
Okay.
To help put a context around the feed that you've created, take the GBT. How are they solving the wide bandwidth problem, and how much do those feeds cost compared to the ones that you've designed?
You mean the GBT or the EVLA?
Well, I meant the GBT, but I don't.
Well,
take the VLA if you prefer. Yeah.
The EVLA just went through a big upgrade, and they have all new receivers. But the way they're dealing with them, they're all octave band receivers, which is typically what people do. You have to have some sort of goofy feed like this to do more than octave bandwidth. And so they have, for every octave, They have a different feed, a different receiver, a different refrigerator. It's complicated.
And expense-wise?
Well, yeah, something like $10 to $20 million was spent on these feeds for the EVLA. The cost of this thing is about, this one, if it were put on an ATA antenna and hooked in and everything, it's about $70,000. So it's very much cheaper than any of the other things.
Cold things tend to gather frost. That's the first part. And then the second part is you have a window, you've got warm stuff on the outside, vacuum, some metal. How do you get rid of the heat in the metal?
It's inside.
On the inside.
Yeah, okay, that's a good question. It's copper that we're using.
Yep.
And that has a number of good features. One of them is that it's a very poor absorber of infrared. If you have really clean copper, only 2%. See, that's hugely important here because that's the only load on the thing, 2%. And with that, all we need is a 5-watt refrigerator. We can take it out, and the temperature drop from the tip to the back is only 10 Kelvin. So that works very well. So so that's the thermal part, and then of course the copper cooled down to that, as I even remarked at one point here, is a hugely good conductor, and so that all helps.
And the frost on the bubble.
The frost. Well, we have this umbrella cover, so we don't see any frost.
And there's vacuum in between, too.
Right.
Yeah, there's vacuum in between. So right, there's a vacuum inside,
Yeah.
and the glass is actually at room temperature,
Yes.
so there's no frost.
Oh, there's that. Yes, okay, you're right.
See, it's just room temperature. We put the umbrella on so that in case it explodes, it doesn't take us out. Oh, it's good to have a little excitement. Not too much.
I'm curious about the refrigeration system you're using. Is it a mechanical refrigerator? And if so, what do you do about the mechanical noise of the refrigerator translating into noise in the antenna?
Right, it is one. It has a moving part in it, and it has a piece of material on it that's weighted so that it tends to take out the vibration of that, and that works pretty well. But it does have a little bit of vibration, but it's quite small. So yeah, that's it.
Just a question: how long it would take for you to cover the Kepler field of view to examine all the possible candidates that Kepler has found?
Well, it's 40 pointings, but see, there's the dimension of what frequency. And see, what we're saying is that the frequency could be anywhere from 1 gigahertz to 15. So that's a lot of frequency space to cover. For the correlator part of it, where we would be using wider bandwidths, like maybe 100 kilohertz even, something like that, the coverage we could probably get over in a reasonable amount of time, and we may be able to do that. So it's not too bad, I think. I mean, it's a finite length project that we ought to be able to get done. And it's important to work at all these frequencies because you just don't know, what they're going to be transmitting. What is their ITU say you can do and you can't do, and all that kind of stuff. Where's their aircraft stuff and all that stuff? Who knows? And my feeling is that they've likely been around longer than we are, and so that they're struggling with our future problems, which we're only just beginning to learn about. So it's hard to know.
They probably have a lot more regulations than we do. One format for wideband transmission is to have a narrow pulse. For example, a 1 microsecond wide pulse on a 2 gigahertz carrier. What would the sensitivity of this equipment be to very narrow pulses like that?
Well, it's spread out in frequency, isn't it?
Yeah.
So that's the bad news in a way, because we get a certain amount of noise per unit bandwidth, and if your signal is spread out over a lot of it, then then it's not as good. And in fact, that's kind of the argument for doing one frequency at a time, because it comes through without much on it. But on the other hand, it doesn't say anything particularly. So it's a bit worse with a wider bandwidth, but I think that's okay. I think it's just going to be a little lower level. People who do communication theory, thinking about how we do that here, say that there are sort of generalized arguments about what sort of modulation schemes you should use, and how you should think of detecting it. And they're optimistic that they can deal with wider band things by taking this point of view, assuming that what they're doing is somewhat universal, and that's kind of exciting.
My question is about the science of the Coma Cluster. What will you be looking for?
Well, we'll be looking for other strong beacons. Actually, we could just take that one beacon and say that we're going to be looking at this thing, and so assume that we know the redshift of it, and then just map the whole thing in CO and see what turns up. Now, they did a little bit of that with the Discovery, because the field of view was bigger than the galaxy. And if you look at their map, it looks like they see a little structure there. So that's kind of exciting. But with enough sensitivity, you see, we could look at the whole cluster in one poke, you see, with the ATA, and just map it in CO at the redshift frequency and see what comes up.
So that has to do with SETI and with hearing signals that are...
No, this is just what's there. See, the things that are redshift of
6.4.
Thank you, 6.5. One of the numbers is rattling around. That's the right number. It's 6.4. So we know what CO1 to 0 will be. That'll be at 15.5 gigahertz. So we just fire up at 15.5 and make a map of the whole thing, and then see how much we see. All galaxies in the foreground have all the kind of stuff that our galaxy has. Molecular gas of all different kinds, lots of CO, lots of all this stuff. So we just fire it up and see what we see, and then maybe we can get a good picture of a really old galaxy cluster and try to understand from that how the evolution has happened or will happen for that place. So it's a real winner.
Are there specific questions with regard to the evolution that are pursued yet, or is this mainly exploratory?
I'm thinking of this as exploratory at this point. Yeah. I'm not embarrassed to be an explorer. Yeah.
Okay, so we just got time for a couple more questions.
Yeah, I guess the rationale for octave wide is noise figure for less bandwidth and better control of the amplifiers. Do they get a lot better noise figure than you get? And my other question is about calibration. To calibrate like a decade wide for a phased array type of thing where you're trying to match phase and amplitude, can you actually do that with all the different errors that are in there?
Well, we look at radio sources, and typically the bright synchrotron radiators broadcast the whole spectrum, which is pretty well known. And so you can just use that for the calibration for anything you're doing.
Calibrate each antenna one at a time, and then bring them all together?
Yeah. We argue about what the best ways of doing this are, but there are different possibilities. You could imagine doing the noise temperature measurement of each antenna, but actually that's a start. That's a start. You could calibrate the one antenna. So here's its gain and here's its noise, and then you put that in with all the others. But I think it works out well if we can do a lot of these things at the same time.
Just a quick programmatic question. I mean, you presented a fantastic design, and you've been testing it. But do we have funding for implementing it throughout the dishes and the ATA? And
not yet.
Mm-hmm.
But we have some, we're optimistic.
Has Mr. Allen heard this?
Well, that's an interesting point. You might say, well, maybe we should go back to him and say, come on, Paul, look at this fantastic receiver. Don't you want to give us a little bit of your change to put all that? He has said that he thinks he's done as much as he's going to do for the ATA, though. That's probably the way it is.
Well, okay, that's all we have time for. Thanks to everyone for coming and join me again in thanking Jack for the talk.